Here we have our code for our path planning algorithms. Starting with distance transform, we are going to create the map of the tic-tac-toe grid, define the waypoints, and then looking at the actual algorithm, we are going to first initialize the distance transform object dx, and um, we are going to initialize an empty matrix to store the computed path. And we are going to print a message indicating that we're running. We are going to start our timer using tick-tock MATLAB function. And we are going to iterate through all pairs of consecutive waypoints. And then we are going to compute the shortest path from the start point to the goal point by querying the distance map. And then if the matrix is empty, the current path is directly assigned. Otherwise, the segment path is appended to the existing path. Like we mentioned before, using MATLAB's tick-tock function, we are going to stop the timer and print the time and our visualized plot. So if we run our code, we are going to see that it's running. We're going to see the time and the number of points, and the figure will look like this. We have our path points in green and our second to last waypoint being the starting point in this case, and our actual starting point also being the ending point over here. Now, if we go to the probabilistic roadmap method, once again creating the map and defining the waypoints, we are going to initialize the probabilistic roadmap planner with 250 sample nodes and a connection radius of 10. We are going to start our timer, and then we are going to generate a roadmap by connecting nodes in free space, querying the shortest path between each of the waypoints, and finally appending the resulting paths into a complete path, while of course measuring the time and visualizing. Now, if we were to run this code, we are going to see the execution time, the number of points, and over here, our plot. Finally, for the D star path, once again, creating the map, defining the waypoints, we are going to initialize the D star planner with the same map one occupancy grid and then calculate the path between the consecutive waypoints, planning the optimal path from the current goal back to the starting point, and dynamically updating the path if needed. In our case, we won't need it since it's going to be a static environment, and we're going to append the computed segments into a complete path while measuring the execution time. So if we were to run this, we see many iterations are being run. It looks similar to the DX transform in this case. And we have our path points in green and our last two waypoints labeled. For our hardware implementation, we're going to start off with our shape drawer function. This is going to be called in another script for our physical robot. But here, basically, we have a function that will create the tic-tac-toe grid with two horizontal lines and two vertical lines, and scaling it properly. In robo move, in this script, we're going to define the properties that we need in our robot, defining the robot itself, Ario, the joint angles, the servo motors, the pen being up and down, and then shape drawer function that we mentioned earlier. We're going to create our robot, draw our grid, and then we are going to plot the grid points using inverse kinematics. We're going to move the robot to those points using inverse kinematics to find the joint angles. And for our Arduino, we're initializing it on adding our servos and starting it in a good position, moving the pen up and down, and moving the servos as needed. For the actual path planning algorithm, we're going to move to RoboPlot, and here we initialize our robot, define the scaling factor, and create the tic-tac-toe grid and define the waypoints before doing the distance transform, which is the path planning algorithm that we chose to integrate in hardware. And this is what the code looks like. Here we have our physical robot Ario creating the grid that's going to be the obstacle that the algorithm wants to avoid. And this is 4 times the speed. And the algorithm that we chose was the distance transform algorithm. And as you can see, the robot is doing a good job of avoiding those obstacles, and it is behaving as expected from the DX form plot that we seen before, just a little less smooth.